Fuels are materials which give off large amounts of heat when burned, in what we know as a combustion reaction. This lab is an experiment exploring the principles of calorimetry, the measuring of heat exchanges in a system, for which we will be testing various fuels. For this video, I will be demonstrating the procedure for this lab, to give a better idea of how it is done. The two main procedures are gas chromatography, mass spectrometry, and calorimetry for fuel comparison. This lab requires the participation of everyone else performing it. There are 12 unknown samples in total. Each group will analyze a single unknown sample with GCMS and 2 unknown samples with a calorimeter apparatus. The measured results for every group will be necessary to complete this lab and subsequent post-lab. Lastly, this lab will have minimal amounts of waste. All heated water will be poured into the lab sink. If any fuel is spilled, it must be disposed of in the non-halogenated waste container. Firstly, your lab TA will give you an unknown sample of a fuel or additive, and you must dispense 10 drops into a sample vial. Make observations on the properties of the sample, such as its color, scent, viscosity and other noteworthy attributes. The sample will then be taken to Shimadzu Education Lab in CPB 113, where it will be analyzed using GCMS. Record the sample number given as you enter the lab. Your results will have either 1 or 2 peaks graphed, with the best fitting substance being applied to each peak. For this unknown sample, the first peak is identified as 1.22, meaning the first best fitting substance is ethanol. The second peak is identified as 2.48, meaning the second best fitting substance is pentane. Write down what your substance or substances were determined to be. You will be needing it later in this lab. You must also take a picture of your unknown samples analysis, as you will need it when you work on your post-lab submission. For part 2 of this lab, you will use an aluminum soda can as your calorimeter that will contain water, which will be mounted above one of the 2 unknown fuel burner samples you will be analyzing. A thermometer will be inserted to measure temperature, as well as a glass rod for stirring. In this experiment, we will be analyzing the fuel burner for isooctane. First, measure the mass of your soda can and record the value. In this case it is 9.14 grams. Next, add 100 milliliters of water to the soda can and remeasure the mass, and record the value. Here it is measured to be 104.68 grams. Then, measure the temperature to the nearest 0.1 degrees Celsius. For this run it is 19.8 degrees Celsius. After this, measure the fuel burner's mass, and make sure that the cap is on the burner when measuring. This gives a value of 106.31 grams. Next, configure the apparatus as it is shown. To reiterate, the soda can with water will be mounted above your fuel burner, held by a glass rod and holding a thermometer above it. The apparatus will then be encircled by a draft shield, so that the flame is stable and does not flicker away from the calorimeter. With this, you are now ready to begin the experiment. Light your burner and stir with the glass rod to heat up the water. Extinguish the flame when the thermometer reads 70 degrees Celsius. Write down the final temperature and immediately weigh the fuel burner afterwards, with the cap on. In this case, our final temperature was exactly 70.0 degrees Celsius. Be sure to collect the mass of your fuel burner, which was 104.51 grams with the cap. Once all the values for your experiment are collected, repeat this experiment once more with the same fuel burner, and twice more with the second fuel burner. With both fuel burners tested twice, you can determine the heat value Q, using the formula MC delta T. The M value is the difference between the mass of the soda can with water, and the mass of the empty soda can, leaving only the mass of water. The change in temperature will be the difference between the final temperature and the initial temperature. The specific heat constant C is given as 4.18 joules per gram Celsius for water. For this example run, we multiply 95.54 grams of water, times 4.18 joules per gram Celsius, times 50.2 degrees Celsius. This gives you a measured heat value of roughly 20,048 joules. To find the fuel value, you divide your heat value by the amount of fuel consumed, the difference between the initial mass of the fuel burner and the final mass of the fuel burner. 106.31 grams minus 104.51 grams is 1.80 grams. We have our final value of roughly 11,137 joules per gram. When rounding down to the proper number of significant figures, this will finally amount to 11,100 joules per gram. These calculations will then be applied to the 3 remaining sets of values. The joules per gram values for each fuel burner will then be averaged and shared with the class. There should be 2 average values for each fuel type, which themselves will be calculated into their final averages. The mixture identities that were derived previously from GCMS will also be shared with the rest of the class.